Okay, so today we are going to start our topic about graphing rational functions and their properties. So on page 8, we're going to pause the video here and I'm going to want you to try this warm-up problem in the box. Okay, so given the graph, we want to identify the vertical and horizontal asymptotes. And it looks like our graph is approaching this vertical line. It's kind of hard to see over here. So let's count this one. This one looks like 1, 2. This looks like the vertical asymptote at x equals 2. Oh, my handwriting's kind of funny. Sorry, I'm getting used to a new tablet. And I can see if I plug in 2 to the denominator, that would make the denominators, or if I plug in 2 to the whole equation, that would make the denominator 0, and we can't divide by 0. So the other way to figure out the vertical asymptote is take the other factor, set that equal to 0, subtract, and that's when x equals -4. So right here must be the other vertical asymptote at x equals -4. Now for the horizontal asymptote, I think I'm going to go by based where this piece is approaching. That looks like the easiest thing to read. Let's count that. 1, 2. Looks like either negative. It looks like y equals equals -3. And that's a good approximation just based on the graph. I'm sorry I'm not there to answer any homework questions. I'm going to pick my favorite one that students normally ask about, like number, let's go with number 8. Okay, so for number 8, let's go with, I have to isolate the expression with the exponents. I'm going to add 1 to the left. That's 27 equals 27x to the 3/4. All right. Then we use the reciprocal exponent. We raise both sides to the power that when I multiply these powers, I get 1. So on the right, we're left with 27x. And on the left, I'm going to rewrite this as 27 to the 1/3 to the 4th. Because 27 to the 1/3, that's the same thing as the cube root of 27. If you like seeing that more as a radical. So what times itself 3 times is 27? That's 3. And now I have 3 to the 4th. So that would be 27 times 3. Oh, you know what? And since we're going to divide by 27, let me write it that way. 3 to the 4th is 27, which is 3 to the 3rd, times 3. And that's going to equal 27x. So now, when I divide both sides by 27, I didn't have to do that extra multiplication. 27 divided by 27 is 1, and we're left with 3 equals x. Okay, now back to page 8. So turn back to page 8. And the definition of a rational function is a function in the form p of x over q of x, where p and q are polynomials. The domain is all real numbers except values that make the denominator 0. So this is what we're going to figure out first. The domain. So I want you to highlight this or circle it. Is all real numbers except numbers that make the denominator 0. All right, number 1. H of x is 2x squared minus 4 over x plus 5. Find the domain. So the domain is going to be all real numbers except whatever number makes the denominator 0. So my denominator is x plus 5. Set that equal to 0. When I solve, so x equals negative 5. The denominator can't equal 0. So the domain is all reals x cannot be negative 5. Okay, so now for number 2, our denominator is x squared minus 4. We don't want that equal to 0. And there's actually 2 ways to solve this problem. You can use the square root method, or you can factor. So I will show you both ways. If I add 4 to the right, so x squared can't equal 4, square root both sides. But now here's the catch with the square root method. When you square root to solve, you need to include plus or minus the value. If I go to factor, this is the difference of 2 squares. So I can factor to conjugates. Conjugates are terms that have opposite signs. So what squared is x squared? That's x. What squared is 4? Is 2. And then the opposite signs, the conjugates, one's a plus, one's a minus. So when we factor, the zero product property says each factor should equal 0, or in this case, can't equal 0. Solve it. So x can't be negative 2. This is adding 2. And x can't be positive 2. Same result we got here. So our answer is all reals. X cannot be negative 2 or positive 2. Okay, 3. Again, I'm not even looking at the numerator, just the denominator. The denominator can't be 0. We have another kind of factoring here. We have a trinomial where the leading coefficient is 1. So we need 2 numbers that multiply to 12 and add to... I'm getting really frustrated with my handwriting, sorry. And add to negative 8. So let's see, what multiplies to 12? 1 and 12, 2 and 6, 3 and 4. And when I pick, since the middle term here is negative, the bigger value has to be negative because positive minus the bigger. When I have a bigger negative and a smaller positive, we get a negative result. So when but is a positive, so Miss Weiss, they all have to be negative. That's my mistake. They all have to be negative. Because 2 negatives multiply to a positive, and here's our pair, negative 2, negative 6, x minus 2, x minus 6, can't be 0, set each factor not equal to 0, solve each one. So our domain is all real numbers. I don't need that comma. I'll make that an x cannot equal 2 or 6. All right, I'm going to pause. I want you to pause the video here. I want you to try number 4. All right, so I got my denominator. Can't be 0. Oops, 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 oops. No square there. All right, so factoring. What two numbers multiply to negative 12 and add to negative 1? You should have picked negative 4 and positive 3. Set each factor not equal to 0. And if factoring, if you're thinking to yourself, oh my gosh, she's making us factor. Yes, we will factor a lot this unit. Factoring is forever. If factoring is causing you some anxiety or some stress, please see me at lunch. Also in Drive, there is a document about solving quadratics with a lot of factoring help. So you can access that there as well for help. All right, so we got all real numbers. X cannot be 4 or negative 3. Okay, turn to page 9. For number 5, we're going to compare the domains of this rational function and this line. So for f of x, which is a line, it's linear. Okay. F of x is linear, so the domain is, and I want you to pause the video, think for a minute, for a linear equation, what would the domain be? Okay, you should have said all real numbers. R of x is rational, and x minus 1 cannot equal 0. So when you solve that, what is the domain? So the domain is all reals x cannot equal 1. Okay, however, I want to show you the graph of these and explain why we're comparing. All right, here's a graphing calculator. We had the line x plus 1. Then we had the rational, which was x squared minus 1 divided by x. Wait a minute. Okay. Minus 1. And look, they line up. The red and the blue. So I'm going to turn off the blue. There's the red. Turn the rational back on. They line up. So it looks like they're the same. That looks like this rational should be a line. However, based on the denominator, we know that x can't be 1. So when I have 1, that's undefined. I wanted to try to click that. Oh, it's here. It's skipping right over it. It won't let, oh, but that was on the red graph. Turn that one off. There we go. So on our rational, there's 0, 1. I can't click on 1, 2. It's just zooming in every time I double click because at 1 it's undefined. Now, why do they look alike? Why do the two equations look the same when they're not? Or why do the graphs look the same when the equations are not? The r of x equation here, we can simplify that. We can factor that numerator. So x squared minus 1, that's a difference of 2 squares. So we can factor to conjugates. Conjugates. Opposite signs, same term, opposite signs. So what multiplied by itself is x squared is x and x. What multiplied by itself is 1. Opposite signs, positive, negative. There's the conjugates. And x minus 1 divides by itself. And this rational function simplifies to match f of x, but it's not a line. There's a hole. There's a hole where that denominator equaled 1, since we know the denominator can't be 0. I said that wrong. There's a hole when x equals 1, because the denominator can't be 0. So we're still going to connect this into the discontinuities from our first unit. We have this removable discontinuity, a hole, when x is 1. Now I can actually find the coordinates of it. When x is 1, and I plug that in, we get 1 plus 1, that's 2. So the hole is the location, is the point 1, 2. But this process of a hole, that's an entire another lesson. We're going to spend actually maybe 2 days just finding holes in rational functions. All right, so let's summarize vertical asymptotes and then get into x and y-intercepts for our final topic today. Vertical asymptotes occur, I'm going to type it, okay, they occur when the denominator equals 0, the vertical asymptote is the equation of the line where the rational function is undefined. Okay, so add that definition in under vertical asymptotes. Pause the video to do that. Okay, so then we've got x and y-intercepts. If I think of a graph, the y-intercept is where we cross the y-axis. Any point on the y-axis has an x-coordinate of 0. So to find the y-intercept, we substitute 0 in for x and simplify. An x-intercept, over here, is the coordinate where the y is 0. So the f of x, the g of x, that's the y. So we set the whole equation equal to 0 and solve. So set the y, which is the entire equation. Even I can't read that. Okay, kind of. So let's do that for number 6 and 7. Okay, I wanted to see what else was sneaking up at the bottom there. All right, so let's focus on number 6, vertical asymptote. That is when your denominator equals 0. So we've got when x squared minus 2x minus 3, where that trinomial equals 0. Take a moment, try to factor that, pause the video and factor. All right, so you should think to yourself what multiplies to 3, that adds to negative 2, and that is negative 3 and positive 1. Set each factor equal to 0 and solve. We get x equals 3 as a vertical asymptote and x equals negative 1. Okay, y-intercept is substitute 0 in for x and simplify. Let me bring this down. Okay. So we're going to substitute 0 in for every x. All right, and simplify. So 0 minus 2 is negative 2. And then 0, now 2 times 0 is 0. So 0 minus 3 gives us 2 over 3 positive. But I need to write the y-intercept as a coordinate. So that's the x-coordinate of 0 and the y-coordinate of 2 over 3. Okay, and then x-intercept is when we're going to set the entire equation equal to 0 and solve. Oh, let me just start with a big 0. All right, equals 0. So now we've got a fraction equal to 0. And when we have fractions, I like to line up numerators and denominators. And when we solve with 0 equal to the fraction, we can cross multiply. So I can say 0 times the denominator, which will be 0. 1 times the numerator, which is x minus 2. Add 2. We get 2 is x. But 2 equals x, that's a line. So that's not our answer. We need a coordinate for the x-intercept. So it's the coordinate 2, 0. All right, one more. Vertical asymptote for 7. Try that now. If you're stuck, let's look back up here. Vertical asymptote. It occurs when the denominator equals 0. So pause the video and find the vertical asymptote. So the plus 7 is not going to affect the denominator. So we've got x minus 5 equals 0. Add 5. Add 5. X equals 5. So the vertical asymptote is the line x equals 5. The y-intercept is anywhere, we replace x with 0. So that's 2 over 0 minus 5 plus 7. So 0 minus 5, that gives us negative 2/5 plus 7. And now we have to add the integer with the fraction. To do that, we need a common denominator. Since the denominator of 2/5 is 5, I want my 7 to have a denominator of 5. But I can't just stick a number in the bottom. I have to multiply the numerator by 5 as well, because 5 over 5 is 1. So I'm not changing the value. I'm just changing the way this looks. So we've got negative 2/5 plus 35 over 5, because 7 times 5 is 35. Let's subtract 35 minus 2. It's 33/5. So the y-intercept is 0, 33 over 5. All right, then we've got the x-intercept. Set your entire equation equal to 0. So now, instead of I forget what problem number, the problem before, where we had one numerator, one denominator, this equation, this rational equation, we have a constant at the end. So first, I have to subtract that 7 to the left to combine the constants, the parts that don't have the variable. So we get negative 7 equals 2 over x minus 5. Now I'm going to want to cross multiply, so I make my 7 into a fraction over 1. I've got 1 times 2, and then negative 7 times x minus 5, where I'm going to distribute. Isolate the x. So here we're going to get x is positive 33 over 7 because negative divided by negative is positive. So we get 33 over 7, comma 0 as the x coordinate. Okay, homework, page 10, just page 10. If you get stuck, pause your brain. You're not going to be watching the video at the point. Look back at your notes. Look back. There's some productive struggle here. You have to take the thought. You have to take the time to process. Look back. What does it mean for the domain? Where did we do that on page 8? Vertical asymptotes. What was that? Where did we do that on page 9? And then the same thing for the bottom two problems. Vertical asymptotes, x-intercepts, y-intercepts. Look at the work we did on page 9 and use that to guide you in finding your answers. Don't forget to check on Drive.